Okay, guys. So, yeah, I think everybody grab a seat. We've got quite a bit of stuff to go through for this lecture in computer programming. What we're going to look at today is essentially 3 lectures on 2 of them. Well, one of them is wrapping up functions, and the other 2 are focused on arrays. Okay, so 2 of the concepts that I would really like you guys to grasp. Obviously important concepts for the test, in view of the test also for next week, so let's look at that. So where we are now in the work is we are busy here with functions over here, okay? And what we're going to look at today is something called recursion, and then look at 2 examples of recursion. In Afrikaans is called recursie, okay? So what recursion is, actually pretty simple. Well, let me just go back here. Firstly, let's just recap what is a function. So a function is when a piece of code can be wrapped up in a block, in an executable block, and then it's called from other parts in the program. So functions, at the moment, before you did this lecture, functions only called other functions. They didn't call themselves. So in this lecture, what the guys reviewed was actually the concept of recursion, all right? And that happened when a recursive function is defined as something that calls itself, okay? Either directly or indirectly through other functions. So that is the key component of recursion, is that it's a function and it calls itself. Can be done directly, so the function can call its own name inside of itself, which is similar to or in line with the examples that we're going to look at now in this part of the lectures, or the function can call itself through other function. Now the whole concept of recursive problem solving actually ties in pretty nicely with engineering, right? And it's similar to what you guys should have seen in something like electrotechniques, where you're busy with at the moment is around superposition. So what we're doing with recursive problem solving is this philosophy where we can only solve very, very simple cases. And we call these base cases. So when a function is called with a base case, then it returns the result of that calculation. We're going to see now with the 2 examples how that works. But if a function What happens then if a function is called with a more complicated case, more complicated part of the problem? Then in recursive problem solving, we break the problem down into smaller, more manageable pieces, okay? And it basically breaks it down into 2 pieces. One that it knows what to do with, and the other one that it doesn't know. So the second part, the one that it doesn't know, has to be simpler or smaller than the original problem. So in effectively, we call this second step, we call that the recursive step, all right? So a function will remain open. That means it will keep on calling itself until it finds this base case where it returns, in which case it then starts returning, and calculating the value. Okay, so if you want to look at a function in a graphical point of view, then you can look at these Russian dolls where one is stacked inside of the other. So essentially the function keeps on calling itself. So here's one example of what recursion looks like, okay, where it can be applied. When we've got to calculate the factorial of a number. So here in this example, we need to calculate the factorial of 5. Okay, so the factorial of 5 is 5 times 4 times 3 times 2 times 1. But this can also be written as 5 times, and in parentheses here, 4 times 3 times 2 times 1. So these brackets. So everything here in the brackets, that can actually also be rewritten as 4 factorial. So we've essentially now reduced the problem, and similarly, we can also write 4 factorial as the number 4 times 3 factorial. So you see this, we've actually been breaking the problem down. 5 factorial, we've broken down into smaller piece, calculate 4 factorial. and so on. Okay, so graphically, this is what it looks like. 5 factorial can be written as 5 times 4, but 4 factorial again like this, and so on. So how are we going to implement this in code? Well, firstly, before we do that, we've got to find a general expression for this factorial calculation. And in general, a factorial n is equal to 1 if n is equal to 1, or it's equal to n times the factorial of n minus 1 if n is greater than 1. Okay, so this is our key. And we've got to write a function to calculate this. And we've got to do that recursively. So when you look at the problem statement here, your hint or your indicative part should be this factorial. That is our function. Okay? So in pseudocode, this is what it looks like. We need to calculate a function that does the factorial of an integer n. Okay? If n is less than or equal to 1, so over here, if n is less than or equal to 1, it should return 1 as the answer. So set the variable to return 1. Otherwise, if it's not 1, that means we can still break this problem down into smaller, more manageable parts. So then calculate the factorial of n minus 1. Okay, so this is what it looks like. If we've got a factorial and we assign it the value long. Now, what is the difference between the value long and the value integer? Essentially, long can just store much larger numbers, okay? So that's why we're using long over here. And then we've got our base case, which if we skip back to our general expression, n is equal to 1, and we've also identified it here in the pseudocode. If n is less than or equal to 1, set the variable to return n minus 1. So we've essentially returned n minus 1. N is equal to 1, x, and we're going to return that. Otherwise, we're not going to return anything. We're just going to calculate. We're going to say the value is n times the factorial. We call our function here again. You see this? So we call this factorial function inside of itself. And its value gets a simplified part now. That is n minus 1. So if we look at our block diagram over here, or our example, we're calling, firstly, we've got a 5 factorial. We say, all right, the value it's not 1, it's not greater than 1, so it skips to the second part of this if statement. Let's take it was 5 factorial, so then it becomes 5 times the factorial of 5 minus 1 of 4. And so it keeps on calling itself until this n is equal to 1. So a very good way to or approach to see what's going on in a function like this. I'm not going to do it, I'm just going to tell you guys, is if you write this out in code, use printf statements during each of the calls. Print the number of n here. So before this long x semicolon and this comment here, right there, printf n. And then you can see, you can see if you can trace how is this function being called. Okay. All right, so another part of the recursive nature, something that works really well, is the Fibonacci series. So that is when you have a number series that looks like this. So 1 is equal to 0 plus 1, or you take the preceding two terms and you add them together and you get this term. So, 1 is equal to 0 plus 1, 2 is equal to 1 plus 1, 3 is equal to 1 plus 2, 5 is 2 plus 3. So pretty simple. Okay, so we begin with 0 and 1 and has the property that each subsequent Fibonacci number is the sum of the previous two numbers. So in general, again, we can express this in general for any number of n like this. So this essentially estimates the Fibonacci series. It says that a number n, like say n is for example the 1, 2, 3, 4th number over here. So what is it? It's n minus 1, so it's a Fibonacci of 3, plus the Fibonacci of n minus 2 of 2. So it says that this number is the sum of that one plus that one. So essentially over here you can also see that the word Fibonacci is featuring on both sides of this equal sign. And that is an indication that recursion would be a very good way to solve this problem. All right, so what we've got over here is we have if n is equal to 0, there it's 0, and if it's equal to 1, over here it's 1. So in order to write this, it always helps to write this out in terms of like a schematic or a drawing. So we see that if we want to calculate the Fibonacci of 3, then if we go back to our formula for a general case, this becomes the Fibonacci of 2 and 1. But in line with recursion is that we're going to break a complex problem up. If it's not at its simplest form, if it's not at one of these cases, those are its simplest form. If it's not at one of those, we're going to keep on breaking it up until it gets there. So F1, cool, that's at its simplest form. So we can just return 1. We just say, okay, this is 1, n is equal to 1, return 1. But if the Fibonacci of 2 is still not in its simplest form, it can be expressed as the Fibonacci of 1 plus the Fibonacci of 0, which then each of those respectively are in their simplest forms, and you return those. So this is what it looks like if you write it in pseudocode. But the best is to look at the program over here. We've got a function called Fibonacci. It also takes the value long here. It's just a very big integer. And we define our base case. So our base case tells us what the value should be set at when the function is returning. Okay? So our base case is identified over here in the values, what we've got here, 0 and a 1. And this is over here. If n is equal to 0 or 1, we set it equal to n and we return. Well, we're not going to return, we're just going to skip this else, and then over here we're going to return. But if it isn't one of those, then it means that our problem is still not in its simplest form. In that case, we have to break it up into smaller pieces so that we eventually get to the simplest form. And that's why we call it Fibonacci. We call Fibonacci here and here again. So each one of these two are recursive steps. Okay, so that's more or less what recursion is, how you can identify problems that can be solved like that, and it typically involves number sequences, right? So these number sequences can be calculated by looking at the same function at a previous part of the sequence. But we can also implement recursion. Iteration is also something that we can implement using recursion. So all problems that can be solved with recursion can also be solved with iteration. Recursion is more processor and memory intensive. However, in most cases, the recursive solutions are more elegant. So I think before we step off this lecture, so firstly let me hear, do you guys have any questions about recursion? Okay, so the best way in which we're going to look at recursion to get you guys going is in this week's practical that's coming. I think it is still coming, right? You haven't done a practical on recursion at the moment. So in this practical on recursion, there's a getting started video already up for it that shows you how to implement a counter controlled for loop. So I loops from 0 to 10 or 0 to 9 or whatever. How you do that with recursion. So please go look at that video and then you'll obviously try to do that before the practical, and in the practical, that's when you guys have a good chance with your code or your implementation open and you don't understand it, then call us and say, okay, what is going on here? But recursion, unfortunately, is one of those things you can't just learn it by looking at the slides here, by listening to me going through the theory. You need to practice it yourself. Okay, so the getting started video and this week's practical is a good point for you to just understand what's going on here. In general, it's not always the best approach to solve a problem. As they said, any any problem that can be solved with recursion can also be solved with iteration. So in general, it's not used that often. However, it makes for beautiful code. But for the tests and exams, obviously you guys have to understand the basic principles of it. So are you sure? There's no questions about recursion? Okay. Now, the second part of the lectures is this over here. It's arrays. So we're going to start off with, this was an introduction to arrays. I think this was the first lecture in which you guys saw arrays. You'll also see it this week in the practical. And in the textbook, we're around about here now, in chapter 6. So progressing quite nicely through it. Okay. In this lecture, you looked at what is arrays, how do you clear it, and also had a couple of examples. Sorry, this thing, I just want to get it right. Okay. All right, so what we have, okay, so what is an array? An array is a structure that stores related data items of the same data type, and it's got a fixed size throughout the program execution. We do, at this point in time, we do, however, have this concept of dynamically allocating more memory if a program should require it, but that is left till chapter 12. We call it dynamic data structures. So for now, your array declared in your program will have a fixed size, and it just groups a bunch of related items in memory. So if we draw it out, so this is this block, what we can see here on the right-hand side. That is what an array looks like in memory. And it starts, this C is called the name of the array, and this square brackets, each one of those are its elements. So this array has 10 elements, but very important, we start here with element at position 0. So in C we index, we call it indexing, we index the array starting from element 0. And then we go element 1, 2, 3, 4, 5, 6, 7 to n minus 1. Not C10 for array element 10, C9 for array element 10. And what will happen, just a side note, if you do try to index the arrays outside of its bounds, then you might get what we call a runtime error. Okay, you've seen runtime errors in one of the first practicals that you did, and you're trying to access memory that the software that you're writing hasn't formally allocated. That memory is actually available for other things in the operating system to use. So that's why you'll get a runtime error for that. So it's very important to take note of the indexing of the array when you work on it. Okay. If we want to, now we can operate on the array. We can operate on each of its elements, its indexes. And we can do that if we've, for example, we have array C and we want to assign a value 3 to element at position number 0. Then we can say C0 is equal to 3. If we want to display the sum of the first 3 elements of C, then we can, for example, say C0 plus C1 plus C2. And that's why it's very important over here. Obviously, it's very important that your elements are of the same type, right? We can't add different types of elements over here. If we want to calculate the half of the 7th element and store the value in X, then we can do it like this. And this is not nice syntax, but you can do that. If you want to perform operations in an index, you can do that. So A plus B, if A is equal to 3 and B is equal to 2, then this operation would just add 2 to the 6th array element. There's also other operators that can be used. So we use the array elements just as variables, and we take note of how we index them. C with a square bracket and an index over here. Okay. Now, when we specify an array, we need to specify its type, just like any other variable. So this C is a integer arrays, int c. So this, we specify its name. This one is called C, this one is called myArray. And then the square brackets, and we also specify the amount of elements, the number of elements that that array contains. So C, an integer array C contains 10 elements, and this array, a float, contains 3,284 elements. And if we have, for example, we want to declare multiple arrays of the same type, here is B and X, then we can just do it using this comma over here. You can do the same with variables. Okay, now what about initialization? So, like other variables, array elements aren't initialized when they are declared. That is something that I think you guys picked up pretty early in this subject. If you have a variable and you use it later on and it's not initialized, it may result in very strange behavior. Okay, so arrays also, if you don't initialize them explicitly, that can cause a significant amount of issues. So what we can do is, one of the options is to use this list here to initialize the array n. It's called an initializer list. We say n has got 5 elements, so we've got 5 initial values, 1, 2, 3, 4, and 5. However, if we don't want to specify each one explicitly, but we want to initialize all of them to the same value, then we can use an initializer list that's shorter, and the remaining elements will become 0. So we just say n all is n, that is, when we declare it, here is where we declare the array, int n 5, there's 5 elements, is all equal to 0. So all of the elements will be equal to 0. But if the size is omitted, then we can also use the initializers to denote how many variables or how many indexes are in this array. So I don't have a size here, but I've got 5 initial values. So this array will automatically get the size of 5. So this isn't very good practice because it means that I'm not keeping track of the size of my arrays in my program. So as you'll see later, when we pass arrays to functions, having the size, passing the size is also something that's very good. Now, all these ways, these manners, I'm not so fond of these ways to initialize arrays because it's not very explicit. Sometimes you'll forget about this. A better approach to initialize arrays is also explicitly to iterate over them and then set each of the values according to what you want. So if, for example, I want to initialize an array with even integers from 2 to 20, and I want to display it later, how am I going to do that? So let's look at this part of the code. It's actually quite neat. We have an array called int s, so our array is called s, and it's of a size here, and size is defined by this hash-defined statement. It's what we call a preprocessor. I'm going to jump ahead a bit in the size. It's a preprocessor directive. Okay, so this preprocessor directive gets, when the compiler works, right, it replaces this word capital size with the value of 10. So it's just a nice way to keep track of my code and to say then, I don't want to change everywhere where this number 10 is in my code when something has got to change. Say this 10 has got to change to 11 or to 12. It's going to be pretty difficult to change it in all these places. A better approach is just to define a constant called size and use that each time you want to refer to 10 elements. Okay, so here we've got our hash define. We declare our array. It's of size 10 here. It's of size. And we're going to loop over each of the elements. So we say we've got a for loop. J is equal to 0. And do this while j is smaller than size. So it's going to start at 0, which is the indexing for the array. Remember, array indexing starts at 0, and then it just increments my index. And to calculate the even numbers, 2, 4, 6, 8, 10, and so on, up to 20, I can use this formula over here. Okay, so I start at 2, and I plus 2 times j. First time j is 0, so this is just 2, and then it goes on. Until j is equal to 9, then 2 plus 2 times 9 is equal to 20. And I print it out. And I use the exact same for loop concept to just print out the individual entries of j. And this print statement over here, just to note that, this print statement has a bit of formatting built into it so that the output comes out nicely in this format over here. Okay, as I said, this hash define value of size is very useful because it makes the program scalable. So the value, if I want to change, I tell you, please now change your program to work on 15 variables. Then if you didn't do this, then you'd have to go through your program and change all the places that you specified 10. And the preprocessor replaces all the occurrences of size in the text before the program is compiled. Okay, this is a pretty long example that I'd rather skip this one and get to the next set of slides, which is on the sorting, because I think there might be more useful questions on the sorting. This problem statement just shows you how to log or how to capture the responses of a couple of students, 1 to 40 students. Each of them can rate food on a scale of 1 to 10. And this program shows you how to use an array, a couple of arrays actually, bins, responses, and so on, to store the results of the rating. So I think this example you can go through on your own. What I would like to do is I'd like to look at how arrays are going to be passed to functions and how do we also search through arrays. So this is the first time, okay, this is the basics of array handling. Do you guys have any questions about this part of the work? Okay. Yeah. Look, like it's the same concept of a variable. I know the compiler sometimes doesn't issues a warning when you don't do that, but it's good practice to always initialize variables. Because if for some reason you replace that code where you read the variable, then you haven't initialized that thing because you assumed something is going to happen later on. And that in programming usually leads to an error. Okay, so I think it's always good practice to initialize something. Yeah, if you do overwrite it next future with something like what you read from a user, then it's absolutely no issue. It's not going to be a problem. So initialization is in general a good approach. Yeah? The example for, sorry, say that again. In slide 6. In what? Okay. Do you know in what slide is this? Or just look there? There. This one. Okay. There is a... Okay, maybe... let me just understand you correctly. Sorry. Oh, is there two for loops? Okay. So the first for loop just initializes the value. All right? So over here, we've got Sj, and we initialize its value. We set its value. Each of the elements we are setting to this over here. It starts off at 2, and then it counts. 2 plus 2 is 4. 2 plus 4 is 6, and so in steps of 2, right? So this just sets this array, Sj. So after this for loop, Sj now contains all those 2, 4, 6, 8, 10, all those cool values. But this for loop over here prints it out. Okay, so here we just print if, percentage 7d, percentage 13d, so we're printing 2 integers. J is 1 integer, that's just the index of the array, and Sj is the value of the array. So this for loop sets the values, and this for loop prints it out. Okay. Okay, I'm going to go on with the last lecture, and then we can leave some time for any question on any of the lectures. Okay, and this is number 15 over here. Okay, so we're still busy with arrays, but what we're going to look at now is we're going to see how strings are actually special cases of arrays. It's just an array. It's an array of characters. Then we're going to see how are we going to pass arrays to functions. That's also something that you guys are going to do this week in the practical, and that's also covered in the Getting Started video. So go through the Getting Started video. It shows you that part as well. And then I want to end off with 2 ways in which to search for something in an array. Because arrays can become pretty big, it's used to store a lot of data that's related. So for example, student numbers, all your student numbers, that goes into an array. And if I want to look for something or for somebody, I say, find me student 1436, whatever. And our code then runs through that massive array. Think how many students are on Stellenbosch, right? A lot, like thousands. Okay, so how do we find that student quickly in an array? So that's why these sorting algorithms are pretty important. And when you advance through your engineering career and you go through, you're going to do a bit of coding as well, you don't want things to take hours when it can actually take a couple of minutes. So that's why these sorting algorithms, one is fast, one is slow. We like the fast ones, obviously. Okay, so character arrays. A string is nothing more but a character array. So we just define an array here. We saw now how it works in the previous lecture. str1, that's a name of my array. I denote it using this square brackets, and I say it's type char equals first. So here, this is actually an array of characters, this string, but the characters, this actually also, if you put it in a char array, it also has this value, this null terminating string value. So string 1, this is just something you have to remember when you work with strings. You don't just have that, you also have this special terminating null character with it. So what I say over here, I can also say using an explicit initializer list, but then I've got to do it like this, also specifying my null terminating character. And just like any of the other arrays functions, I can access its individual characters, like for example, str1, 3 is the character S. So that's 0, 1, 2, 3. There we go. That's the S. So in scanf, when we call scanf, we want to store this string into this variable string 2, and string 2 is an array. We don't have to pass this ampersand, this and, because scanf already, this array name is already its address. And this statement is going to read characters until you enter a white space character. Okay, so what we want to do is we want to just see how that works. We've going to read a string, which is an array of characters from the keyboard, and we're going to combine it with a hard-coded string. And then what we're going to do is we're going to print the string that we read from the keyboard. We're going to try and insert white spaces between each of the letters. So this is pseudocode, but that you can read through that. I want to look at the code over here. So what we're going to do is we're going to start off our program, include standard i.h, and then we start off our main. We've got 2 strings. The first string, string 1, has got 20 characters. Let's say that's the most characters that we're going to estimate on receiving from the user. Okay? And the string 2, we're just going to initialize with a fixed value. Just call it string literal. Okay? And this, how big is this string 2 character array? Now, as I said in the previous slide, it is all of these characters plus 1 for the null terminating character. Okay, so I'm just going to use a temporary variable here, and setPuff just fixes everything for output. Now, I'm going to prompt my user. I'm going to say, enter a string. And then I'm going to read something from him or her until they enter the white space character. And the return value I'm going to store here in string 1. So string 1, I've declared to be a maximum of 20 characters big. and I'm assuming that he doesn't type more than 20. If he does type more than 20, then it might result in a segmentation violation or a violation because we're trying to write to memory that isn't there. So, but let's assume that this user is going to just enter less than 20 characters. So what we're going to do then is we're going to print the output strings. We're going to say string 1 is this one that the user entered, and on a new line, string 2 is this string that we've declared. And then what I want to do is I want to also, for the string that the user enters, see if I can separate each of the letters using a white space. And how am I going to do that? Well, we're going to do that because a string is nothing more than an array, right? So we can actually look at each individual character in that string. And this is what this for loop does over here. We start at 0 because our C arrays, we start indexing at 0. Then we say we're going to continue this for loop while we haven't reached the null terminating character. And then we're just going to increment our index. So what we're going to do over here is we're going to print the character with the space. And then print out the as an argument, we take just the indexed array, the character array. So this space will cause this, what you see over here. Okay, so in this part of the solution, we just handled the string array as a normal array, looped through all of the individual entries of the array, and printed the character followed by a white space. Okay, now we're going to see how are we going to take an array, any array, can be int, can be char, and so on, and we're going to pass it to a function. So what we're going to do is we're going to, here's my function, this my function with the bracket, my array, comma, and this 24. This 24 is the size of the array. Because remember, when I told you that if we say an array is 5, has got space to store 5 elements, and I'm going to try and access the 8th element, that's going to result in a runtime error. We're not allowed to do that because we told the compiler we're going to use 5 pieces of memory. Okay, so that's why in a function, when you pass an array in a function to a function, it's good practice to also pass its size. So that's what this 24 is. It's its size. Because if we loop over the array, then we're going to do it. We're going to loop 1 to the array elements that you put over here to make sure that we access only the amount of memory that we told the compiler we're going to use. Very important, array arguments are also passed in what we call by reference. So that means that if we operate on the array element inside the function, then its value changes. So if we return from the function to the caller routine, then the array would be modified unless we do something else. We'll look at what we do, what we can do to avoid that a bit later. So, yeah, so our address of the array is this name of it. That is the address in memory of the first element of the array. Now here's an example where we've got an integer array b, and we pass it, and we also pass the array size. But here is a way in which we can avoid this array b from being modified. And we can do that by using this const keyword. So if our intention isn't to modify the array at all, we can say void my function const int b and the array size. So it looks exactly the same. We just preceded using this const keyword. Okay, but what about values? So what happens if I just want to I want to say that don't use my whole array, just use the value of the first index or the third index or whatever. Well, then I can just index my array and pass that to the function. But in that case, that value is passed call by value. Okay, that means the function makes a copy of it, and it operates on the copy, and when the function returns to the caller routine, then that array index value, that variable, hasn't been changed at all. So I think it's very important that you guys understand the difference between call by reference and call by value. Not just for arrays, but also for any other variable. Okay. All right, so that's the first part of arrays and how it's passed to functions. You're going to see that in the practical this week, and you also got a getting started video for it. Do you have any questions about this part before we get to the sorting? Okay, so the sorting, as I said, when we have a massive amount of data, like for example, all the students in Stellenbosch, all stored in one big array, how are we gonna search through it? Because we want to find a specific student number. How are we going to look through this data? So there's two well-known techniques that can be used. One is a linear search. So the first approach is pretty logical. You're going to take your student number, you're going to look through this massive list of student numbers and compare each one to that. And say, if it is match, yes, I found it. But that's, okay, let's look at that one first. So compare each element of the array with the key value, like I told you now, and it's useful for small and unsorted arrays. Because remember, each of those steps, right? So each of those, if student number that I get from the array is equal to the student number that I'm looking for, that little if statement takes a couple of milliseconds to execute. Now, if you've got 1,000,000 times a milliseconds, you can see clearly that the time is going to increase. So we say that the time scales in n. Okay. And what we do assume here is that we have unique key values. So obviously we assume that there isn't two students with the same student number. It's going to cause a significant problem. But the array doesn't have to be sorted. So we don't care what the order is of the array. We just compare each element to our key value and see if that is it. So in code, this is what linear search looks like. We have a constant interarray. So remember what we looked at, what I told you is that this constant keyword prevents this array here from being changed. And we have a key. That's the key to which we want to compare our elements. And then we have the size of the array. So the size of the array is used in this do while loop. So I'm going to iterate. I'm going to keep on going until while the number of elements, my counter, n is my counter variable, is less than all the entire size of the array. And I can also, now, the other thing that I've got to specify is I'm going to terminate when I actually found a match, right? So to do that, I use this key location variable. Key location is equal to -1. So this do while will continue while we haven't found anything. But if we do find something, like here, array n, so this student that's stored in the array is equal to the key. Now update, I found my key location. This while loop will then terminate because key location is not -1 anymore, and it just returns this value. Okay, so this is what linear searching is. It searches linearly through the array. But if you have a massive array, a big array, it's useful to first sort the array into values, right? So all the student numbers get sorted in some form of an order, like alphabetical order or whatever. And then what we do is we split the array. So we say, okay, let's compare the element that we want to look for, our key value. Let's compare that to the array element in the middle of the array. And if it is not that, well, I can then look, if the key is less than that in the middle, go look in the lower half. If it's larger than the middle, go look in the top half. So the most critical component here is that binary search will only work if the array is sorted. If it's not sorted, it won't find an answer. It'll run indefinitely, it'll get an infinite loop. So, but it's very fast, and it's also much more efficient than linear searching. Okay, so this is just a graphical illustration of what it looks like. So we've got an array of, how many elements do you guys think do we have here? 16, yeah. We've got elements starting, because array in C starts from 0 onwards. Okay, so don't make that mistake. Starting with 1, or, yeah, we've got 16 elements over here. So, and the element that we want to look for is number 11. There we keep two counters for binary search. We say we keep index of the low part of where we're searching, and we keep part of the high index of where we're searching. So the low index is index number 0, so array element number 0, and the high part is array element number 15. And I'm looking for a value of 11 in this thing. So if I look through my array, I see, okay, 11 sits right about there at C4. How am I going to get to it? So the first thing it does is it locates the middle. It just says, well, it's the index low plus high divided by 2. This will be 7. And it's integer division in C. So remember how integer division works. That's how we get to the 7 here. And then I look at the value stored at 7. It's 16. So is 11 greater or smaller than 16? It's smaller than 16. So I adjust my I. Look at this. I adjust my I index to fall in this range. So I reduce my range. I'm now only going to bother looking in that part of the array. So what I'm going to do now is I'm going to calculate my middle again. This is 0 plus 6 divided by 2 is 3. So I'm going to look at array element number 3. Now it's 7. I say, okay, is 7 less than 11? Well, it's smaller than 11. So I got to adjust my low in boundary to fall here. So now I've reduced my search space to this part over here. And then I try again. I say, let's find the middle of that. This is equal to 5. Now do it again. And then finally, I find my element. There we go. And I return it. The key with this searching function methodology is that it will only work when your array is sorted. If it's not sorted, it won't work. But it will work very fast in that case. This is what it looks like in code. I think the best for you to understand it is actually to go implement it and print out your index for the low value, print out your index for the high value, for the indices, and see how it converges. Print out the middle as well. Okay, try different values for the array elements. Okay, so that's what you did in this lecture. I think that about wraps up the lectures that you guys did, the review lectures for last week. Do you have any questions? Okay, if not, then good luck for the test week. I'm sure it's going to go well. Yeah. I'm not sure. You will have to check with your lecturers. So I think you still have tomorrow and Friday lecture, right? Do you have to lecture tomorrow? Jy het nog 2 oor. Okay, you still have 2 lectures left. So the best is to ask the lecturers. I'm just the assistant lecturer. Okay.